This problem is about a weight attached to a spring with a damping mechanism. The problem gave us the period of vibration, which is 1.8 seconds, the spring constant, the ratio of consecutive amplitudes, and the force that is applied on the system. The problem is asking us to find the amplitude and phase when that force is applied. First, we're going to establish what is the equation that gave us the amplitude of the system. The equation that gave us the amplitude of the system is as follows. Notice that to solve this equation, we are going to need the frequency and the natural frequency. Notice that the amplitude of the force is given by F naught, which is equal to 2, which is equivalent to this term in the equation of the exciting force. This is the amplitude of the force of F naught. The stiffness is also given 525 newtons per meter. So again, we only need to find the frequency and the natural frequency to solve for the amplitude. So let's find first, let's work with those terms. And let's find first what is the natural frequency. To get the natural frequency, we can see that we were provided by the ratio of consecutive amplitudes, which that value is equal to 4.2. The equation that relates the ratio of consecutive amplitudes with the damping ratio is given by the logarithmic decrement equation, which is equal to the natural logarithm of the consecutive amplitudes, and at the same time is equal to 2 pi damping ratio over the square root of 1 minus damping ratio squared. From this equation, we can find the damping ratio. So let's do that. If we solve for this equation, we are gonna have that the natural logarithm of this ratio is equal to 1.435, and solving this equation by damping, we're going to find that the damping ratio is equal to 0.223. Okay? Now, how we relate the damping ratio to the natural frequency? We do that by the following equation. The frequency of damping is equal to the natural frequency square root of 1 minus damping ratio. Or the natural frequency is equal to the damp frequency over the square root of 1 minus the damping ratio, square of the damping ratio. Now, what is the damp frequency? The problem indicates that the period is equal to 1.8 seconds. So the frequency is related by the period by the following equation. So 2 pi over period is equal to the frequency. So therefore, 2 pi over 1.8 seconds is gonna give me the damp frequency in radians per second. Therefore, the WD is equal to 3.5 radians per second. Now, substituting this value into the equation, this equation where it relates the natural frequency with the damping and the damp frequency, we can find the natural frequency. Therefore, natural frequency is going to be equal to 3.5 over 1 minus 0.223 squared, which is the damping ratio we previously found, which is equal to 3.59 radians per second. Now we have the natural frequency that we need to substitute in this equation. We still need to find W. So that W is the frequency of the force that is applied. So the frequency of the force is given by this value, 3. Therefore, we're gonna just determine that here. So we already know that we have the natural frequency, and the W is equal to 3 radians per second. Now we can substitute all of these values into the previous equation that it was previously shown, which is equal to F naught over K square root of 1 minus W over Wn square, and this term is square as well, plus 2 damping ratio W over Wn square. And when you substitute the value there, you're going to find that the result is 0.797 centimeters. That's the amplitude. The equation for the phase is given by the following equation. The angle will be the inverse tangent of 2 damping ratio W over Wn over 1 minus W over Wn square. Again, we can substitute all these values that we found previously, and it's going to be equal to 51.43 degrees. For more content on solving other engineering vibrations and control problems, you can subscribe to my channel. Thank you.